Hello, today we're continuing in our series of A-level physics revision looking at the subject of pulleys. Now this is a subject which is not in all the A-level syllabus, it is only in some, and it's in fact more likely to be found in the applied mathematics syllabus, but for completeness I'm going to deal with it here. First, let's just consider what we mean by a pulley system and the elements of it. A pulley is essentially a rotating disc in which a rope can be placed. So there's usually a groove in the disc to enable a rope to be placed such that it can run smoothly over the pulley. And then in this particular example, I'm going to put masses on either side of the pulley so that we have, say, a mass capital M on one side and a different mass, little m, on the other side. Now for our purposes there are certain constraints. The first is that the pulley is frictionless. You lose no energy as a result of the friction about the pivot point. Neither do you lose any energy through friction as the rope goes round the pulley. That's the first thing we always assume. The second thing we always assume is that the rope itself is massless. Otherwise that's going to contribute to the overall mass of the system. So we assume a massless rope, and we also assume that the rope is inextendable, which means it's not elastic. It retains its same length. Now the consequence of assuming that it's inextendable is that the tension in the rope must always add up essentially to zero. Obviously, if you put two masses on the end of this rope, the rope will be taut. There will be a tension in the rope. What we say is that the result of this mass acting down will be a force, and the force will equal mg, because the force is always the mass times the acceleration, and we're assuming we're in a gravitational field where the acceleration is g, and the force acting down here will be little mg, and that means that there will be a tension in the rope, and we have the tension acting upwards, and it's always T. The reason it's T is that when these two T's meet, they cancel out, so the net tension in the rope is zero. Why can we not have different tensions in the rope? Well, let's suppose that we just take an ordinary rope like this. We're not putting it over a pulley at this point, but we're going to apply a tension 2T in this direction and a tension T in this direction. Well, if that's the case, there is a net force acting on an element of the rope. Let's assume that it's that element of the rope there. And that would mean that that element of the rope would accelerate, because there's a net force, and the net force will cause acceleration. Not acceleration overall, but the acceleration of an element of the rope. And that's elasticity. In other words, this piece of the rope would accelerate away from this piece of the rope. But we have made it a rule that there's no extent, the rope is inextendable, so that it is not elastic. Consequently, there can never be a net tension in the rope itself. There can be tension in the rope, but the net tension amounts to zero. Otherwise, the rope itself would expand as a kind of an elastic, rather like an elastic band. So given that that's the rule, we now want to ask ourselves, what will happen in this system? Well, if capital M is greater than little m, we know that this will move downwards, and of course this will move upwards because the rope is inextendable, so as this moves down, so this will move up. And we want to know what is the net acceleration of this mass, and indeed the same will be the acceleration. This will be an acceleration downwards, this will be an acceleration upwards. What is the net effect? Well, let's first of all look at this side of the equation, and on this side of the equation we've got that the force acting down, which is capital mg, minus the tension in the string is the tension in the rope is the net force acting down, And that is going to cause this mass m to accelerate. So that's the net force, and the net force is simply the mass times the acceleration. And the acceleration is the acceleration by which this mass will come downwards. Let's now look at the other side. This is going to move upwards. The net force upwards is T minus the net force downwards, which is little mg. And that is going to be equal to the acceleration times the mass of this mass going upwards. So that's going to equal little m times a. Now if we take those and regard them as two simultaneous equations, what we can do is to add both sides. So we add these two sides together and add those two sides together, and they will be equal. So we've got mg, capital Mg, and then we've got a minus t plus a t, so the t's cancel out. And then here we've got a minus little mg is equal to, now add these two signs of the equation, and you've got big Ma plus little ma. And we can simplify this by saying that is g into m minus little m is equal to a into m plus little m. And that means that a, the acceleration that we're after, is equal to g into m minus little m divided by m plus little m. So the acceleration by which this mass will move down, and similarly this mass will move up, since they're both going to have the same acceleration because they're connected by an inextendable string or rope. The two accelerations are given by this formula here. Notice that A is not the same as G. In other words, this mass will not fall with an acceleration equal to G. It is falling with an acceleration that is given by this formula here. Now notice a few things. Firstly, let's suppose that m equals m. If both masses are the same, then m minus m will be 0 and a will be 0. And all that means is that if both masses are the same, then they will balance. There will be no net acceleration either way. They won't move. What happens if little m is 0? Well, if little m is 0, then you've got g into capital M divided by capital M, because little m is 0 in both cases. And that means m over m cancels and a equals g. So if little m is 0, then as you would expect, you've just got a single mass falling under the effect of gravity. So it's essentially, its acceleration will be g. But in all other cases, to find the acceleration of the two masses, one downwards, the other upwards, they are given by this formula here. Pulleys can be used to lift very heavy loads that you normally wouldn't be able to lift. Let's see how. For example, let's take a very heavy mass, capital M, which is sitting on the floor, and you want to pick it up. Now, the usual way of picking it up, of course, would be to bend down, grab hold of it, and lift it. This mass exerts a force downwards, which will be capital Mg. So that's the force that is pulling it down. It can't pull it through the floor, but it can pull it downwards. If you want to lift it, if you're going to have an effort to lift it, you're going to have to exert a force of greater than mg in order to get this mass to lift upwards. And if that's very heavy, then you may not be able to exert that force. Can a pulley help? Well, let's think about what you might do. You're going to need a fairly strong ceiling to which you can attach a pulley. And then here is our mass sitting on the floor. And now what we can do is to attach a rope to the mass that goes round the pulley, and you simply pull the rope like that. Does that help? Well, once again, we've got the force, mg, acting down, and we will then have a tension in the rope. But as I've explained, that tension must always be the same, so there'll be a net tension here of T. And you are pulling in this direction with a force F. So F will have to be greater than T, and T, of course, is simply going to be the weight of the object. So once again, you're going to have to exert a force of greater than mg in order to lift that weight. It's marginally easier because at least you don't have to bend down and possibly rupture your back, but it's not really a solution. It's slightly easier to pull down, but you're still having to exert a force of greater than mg if you want that mass to lift off the floor. So we haven't really got very far. Well, let's design a different system. Once again, we're going to have the ceiling, and once again, we're going to have a pulley attached, permanently attached by a steel brace to the ceiling. So that's not going anywhere. And on the floor, we're going to have our heavy mass, which again is mass M. But to this mass, we're going to attach and fix a pulley. So that pulley is actually fixed by a metal bar to the mass. Now I'm going to attach a rope to the, not to the pulley itself, but to the axle or the axis of this pulley. We're going to go round that lower pulley, round the top pulley, and I shan't draw the little man, but you know that he is going to be pulling down with a force F. Now let's put the tensions in the rope. By convention they will go upwards, and the tensions must always be the same. Remember, the rope is inextendable, so the tensions must always be the same. And wherever the tensions meet, they must cancel out because there can be no net tension in the rope. So you'll notice here, these two tensions meet and cancel. Here, these two tensions meet and cancel. So the net tension is always zero. As before, the force acting down is going to be mg, the mass times the gravitational pull, g, that's the force. Let's have a look at this bit of the rope here, this little section here, where we can clearly see that F is equal to T. But if we look at this main section of the pulley system, we see that acting down, we've got the force mg, but acting up, we've got tension plus tension. We've got 2T. And consequently, we can say that T is equal to mg over 2. But T is the force that you have to exert to lift this mass. What we've shown is that the force you have to exert is only half the weight or the force that is acting down. In other words, you could put a mass on this rope which was a half of this mass. It would have to be just slightly more, and that would make this mass rise. So you can make a heavy load rise with this system, which is sometimes called a block and tackle. You can make this system rise by exerting only half the force that the actual heavy mass is exerting downwards, because you are essentially supporting that force with two lengths of rope, each of which have got tension T, and those tensions, 2T, have got to be equal to, or actually of course just slightly greater than. When I put equals, that will give you equilibrium, balance. If you have just slightly more force than mg over 2, then you will be able to lift the weight. Now that sounds like a free lunch. When you've got a heavy load, apparently you can lift that heavy load by exerting just half the force that the load is exerting, or to be accurate, slightly more than half the force that the load is exerting downwards. where's the catch? Well, let's suppose that that load is lifted through a distance of 1 metre. What happens? This length of rope will slacken by 1 metre because the pulley's going to move up by 1 metre. So that length of rope will slacken by 1 metre, and this length of rope will slacken by 1 metre. So you've got 2 metres of slack to absorb. That means that you've got to pull this rope down through 2 metres. So when the mass lifts by 1 metre, you are actually going to have to pull it by 2 metres. And now let's have a look and see what the work is that is done. Remember that work is force times distance. So on this side of the equation, we've got a force which is mg going through a distance of 1 metre. So on the left-hand side, the work done is mg times 1 metre. On the right-hand side, the force is going to equal T, which is mg over 2, but you have to pull it through 2 metres. So the work done will be the force, which is mg over 2, times the distance, but you have to pull it through 2 metres. And you'll notice that those two are the same. They both come out to mg. And work is, of course, the same as energy. So what we've got here is energy conservation. You can lift a heavy weight using only half the force that the weight is exerting, but the price you pay is that you have to pull through twice the distance that the weight will actually rise. In practice, that's not a serious problem for us. That's why we use the block and tackle. But that's the price. I'm now going to draw precisely the same arrangement that we just had. You'll recall that it was a pulley fixed to the ceiling, and then on the floor we had our very heavy mass M, and we attached a pulley to that. But in the previous arrangement, I started by connecting a rope to this axle, or axis, and then we went round the lower pulley, around the top pulley, and we pulled it downwards. What happens if I attach the rope instead to the axis of the bottom pulley? And then I go round the top pulley, round the bottom pulley, and now I pull upwards instead of pulling downwards as I did in the other example. Well, let's put in the tensions of the rope, always pulling up. We've got tension, tension, tension. You'll notice that all the tensions have to be the same because the rope is inextendable, and wherever these tensions meet, they cancel out. So there's no net tension in the rope. The force acting down is mg. But now what is the tension acting up? We've now got 3 tensions acting up. So at equilibrium, where there's no net force either way, mg, which is the force acting down, will equal 3t. That's equilibrium. And you'll see that the force that I have to pull here is going to be equal to T. So my force that I am exerting, the effort I have to make, is equal to T, because that's the tension in the rope here. But that means that since if mg is 3T, that means that T is mg divided by 3. That means that in this arrangement, I only have to exert a tension or a force which is 1/3 of the mass that I'm trying to lift, or more accurately, 1/3 of the weight of the mass, which is 1/3 of mg, just by putting the rope round a different way. And we have a concept which is called mechanical advantage. And the mechanical advantage is always described as the load, which is the force associated with the mass you're trying to lift, divided by the effort, which is the force you have to exert to pull the rope up. And in this case, you will see that the load is mg, but the effort, what you have to put into the rope, is mg over 3, and that equals 3. So the mechanical advantage of this pulley system is 3. What that means is, when you've got a mechanical advantage of a certain number, in this case 3, it means that whatever effort you supply, you can lift a load that is 3 times greater. But the price you have to pay, of course, is that you will need to pull the rope 3 times further than the mass will actually rise. So if this mass goes up by 1 meter, this rope will have to be pulled through a distance of 3 meters, because you've got 3 elements of rope, each of which will slacken by 1 meter as the mass rises. So a mechanical advantage of 3 means that whatever effort you can supply, you can lift 3 times that amount, but you will have to pull it through 3 times the distance of the amount by which the mass will rise. Well, let's see if we can make the system even better. Once again, we're going to have a ceiling to which we're going to attach a double pulley. So we're going to have a large pulley here and maybe a smaller pulley here. They are connected by a steel bar. Right, so these are fixed pulleys. They can't move respective to the ceiling. And on the floor, we're going to have our very heavy mass, M, to which we're going to attach with a steel bar another pulley. Okay, so these 2 pulleys are fixed by a steel bar to the ceiling. This pulley is fixed by a steel bar to the mass. Obviously, the pulley will move up with the mass as the mass rises. And what we do is we attach the rope to the axis of this lower pulley. We go round the small pulley, round this pulley, round this pulley, and then we pull it down with a force F. That is the effort that we are going to put in. Now let's have a look and see what we've got. Tensions, of course, by convention, upwards, always the same, and always cancelling out where they meet. And of course there will also be a tension in the rope here. On this side you can see quite clearly that at equilibrium, F equals T, we always work out what the equilibrium position is first, and then we say that if you want to lift the mass, you have to put in a little bit extra force than the equilibrium position. What about the equilibrium position on this side? Well, we've got a force acting down, of course, as always, of mg. So the force acting down is mg. What is the force acting up? It's 1, 2, 3t. You've got 3 tensions because you've got 3 elements of rope, each of which have got the tension T in them. And so once again, you've got the position whereby T is equal to mg over 3. But T is the force that you have to exert in order to have equilibrium. If you exert a force of slightly greater than mg over 3, you will lift this mass. So essentially, by exerting a force of just over 1/3 of the weight that you're trying to lift, you'll be able to lift the weight with this system. And that, of course, means that the mechanical advantage, once again, is equal to 3, because you are lifting a load which is 3 times greater than the effort you put in. But the price, remember, is that you will need to pull it through 3 times the distance that the load is lifted. That's really all there is to it. So what I'm going to do for the remainder is just to show you other pulley systems that we can design. So we start with the, as before, a double pulley connected to the ceiling. This is where the 2 pulleys are connected by a steel bar, so they are fixed to the ceiling. And on the floor we have our heavy mass, to which we connect by steel rods, 2 pulleys. So we now got 2 fixed pulleys connected to the ceiling and 2 pulleys connected by a metal bar to the mass itself. The mass is of course mg. And now what we do is we start with the rope attached to this axle and we go round this pulley, round this pulley, round this pulley and round this pulley, and we pull down with our effort or our force there. Once again we're going to have a force acting down, which is of course just mg, that's as usual. Now we need to put our tensions in the string. By convention we always put them pointing upwards. They're all T, and wherever they meet they cancel, so the net tension in the rope is 0. We can see that on this particular side at equilibrium the force we have to exercise to pull will equal the T, the tension in the rope. But here we've got a force acting downwards of mg, but a force acting upwards of T plus T plus T plus T. We've got 4 elements of the rope, each of which have got the tension T in them. So the net force acting up is 4T, which means that T is equal to mg over 4. And T is the force you have to apply essentially to get this mass to lift. Strictly, it's equilibrium. If the force is just slightly more than mg over 4, you can lift this mass. So now we've got a mechanical advantage of 4, because the load is mg, but the force you have to exert is mg over 4, only a quarter. So the mechanical advantage is 4. You can lift a load which is 4 times greater than the effort you can put in. But the price, of course, as usual, is that you will have to pull that rope through 4 times the distance that this mass will actually rise. Here's a slightly different system. Once again, we rely on a strong ceiling from which I'm going to suspend 3 separate pulleys. And on the floor, I'm going to have a very heavy mass, attached to which are 2 pulleys. So attach 3 pulleys by steel bars to the ceiling, attach 2 pulleys by steel bars to the mass, and that mass is going to exert a force down of mg. Now I attach the rope firmly to the mass and then I take it over the pulleys. Over, under, over, under, over, and I pull down here with a force F. That's the force I have to exert on the rope. Putting the tensions in by convention upwards, they are always the same tension because you can't have different tensions in the rope, and they always, wherever they meet, they net off to 0. On this particular bit of the rope here, you can clearly see, as usual, that F equals T. So the force I have to exert is equal to the value of T. But here you'll see that the force acting down is mg, but that force is supported by 1, 2, 3, 4, 5 elements of rope, each of which has the tension T. So T is equal to mg over 5. And what that means is that the mechanical advantage is 5 because I can exert a force and lift a weight which is 5 times that force with this arrangement. Once again, the price, of course, is that I will have to pull that rope through 5 times the distance that the mass itself will rise. Why? Because when you lift this mass through, say, 1 metre, each of these 5 elements of the rope will shorten by 1 metre. That's a total of 5 metres slack. That 5 metres will have to be taken up if you're going to keep the rope tight, which of course you need to do if you want to maintain the tension, by pulling this through 5 metres just to get the mass to rise by 1 metre. For completeness, I want to consider a situation that I have considered in more detail in the video that I did on friction. And if you look that up and go to the time 13 minutes and 15 seconds, you'll find this explained in greater detail. But I'll just revise it and rehearse it here for completeness, because this also assumes a pulley. What you have is a plane, this is the surface, which is at an angle alpha to the horizontal, on which you place a heavy mass M. You connect that mass M to a rope and you swing it over a pulley. So it goes over the pulley, comes down the other side. The pulley, of course, is connected firmly to the ceiling, and on this side you have a mass little m. And the question you're often asked is, what are the conditions that will determine whether the masses will move? Of course, one option is that this mass will move down the plane and this mass will move up, so it will go like that. Another option is that this mass will move downwards and this mass will move up, so it'll go like that. Or maybe it won't move at all. And what you usually have to take into account is friction. And we remember, and this again is covered in more detail in the video on friction, that the maximum frictional force, Ff max, is equal to the coefficient of friction times normal force, which is mg cosine alpha. The reason is, of course, that the normal force acting in this way is equal to the force acting in this direction. Well, the force acting downwards, of course, is just mg. That angle there is alpha, and so this is mg cosine alpha, and the normal force is equal and opposite to mg cosine alpha, because there is no acceleration in this direction, because there's no net force. So the normal force acting upwards is equal to the coefficient of the weight of the force acting downwards in this direction. So the normal force is mg cosine alpha, and the frictional force is always the coefficient of friction times the normal force. The direction in which the frictional force acts depends. It always opposes motion. So if this mass is coming down the plane, the frictional force will act up the plane. If this mass is moving up the plane, the frictional force will act down the plane. So it rather depends on which way you're going. So now we can say that there are 3 different situations you can imagine. Let's imagine first of all that this mass is going to cause the whole thing to go like this. So this mass is going to go downwards and this mass is going to go up the plane. What is the force acting in this direction? That will be mg. And mg will have to be greater than, if it's going to move down, will have to be greater than the forces that are trying to stop it. Well, one of the forces trying to stop it is the mass acting in this direction. And that, of course, will be, the weight acting in this direction, the force acting in this direction, is going to be mg sine alpha. The weight acting down is mg, the coefficient of that is mg sine alpha. So that's one of the forces. Mg sine alpha. But there's another force acting in this direction, and that's the frictional force, because the frictional force is opposing the mass attempting to move up the plane. So there will also be a frictional force, which we've calculated, and that's going to be the coefficient of friction times mg cosine alpha. So if mg, which is the force acting downwards, is greater than the 2 forces, the coefficient of the weight acting down the plane plus the frictional force acting down the plane, if that is the condition, then this mass will move down and it will drag this mass up the plane. We can also consider what happens, what are the conditions for this mass to move down the plane. Well, if that's the case, the force acting down the plane, which is mg sine alpha, must be greater than all the forces that are trying to get it to go the other way. Well, what's the force trying to get it the other way? Firstly, you've got this force here, which is just mg. But you've also got a frictional force that will oppose. If this is trying to go down the plane, the frictional force will be acting up the plane, and the frictional force is given here as mu s times mg cosine alpha. So if capital Mg sine alpha is greater than little mg plus the frictional coefficient mu s mg cosine alpha, if that is the condition, then this mass will move down the plane. And if neither of these conditions is met, and that's perfectly possible, then nothing will happen. They won't move. And that does not require capital M to equal little m. They can be different masses, but still not move because the frictional forces are sufficient to stop them from doing so. And what you will often be asked in an exam is you'll probably be given some of this information. You'll probably be given, say, the angle. You'll possibly be given one of the masses and maybe a coefficient of friction. And you'll be asked to identify what mass do you need in order to pull this up the plane. The thing to remember, of course, is that the tensions in the rope are always the same because it's an inextendable rope. So all that is happening is really that the forces are being transmitted through the rope. There is no net force in the rope. The rope is just a means of conveying the force from here to here. The final element of pulley systems that I want to look at today is gearing. Suppose you have a small wheel and you want to turn it. Well, you could put pedals on this, rather like a bicycle, and you could get on the, as it were, get on the system and start pedaling. But you'll notice that your feet will have to go round as fast as you want the wheel to go round. So if you want the wheel to go round fast, you're going to have to pedal. Every time you pedal round one revolution, the wheel goes round one revolution. So if you want that wheel to go round 20 revolutions a minute, you are going to have to pedal 20 revolutions per minute. And that might be quite a lot of effort. But here's a way to make life a little easier. Let's take the same wheel that you want to go round very fast, and we'll take another wheel, which is a much bigger wheel. That should be circular. And we're going to connect the pedals to this wheel. But what we're going to do is we're going to put a rope, a tight rope, so it's taut, around the whole thing. And let's assume, for example, that if the diameter of this wheel is little d, the diameter of this wheel is 4 times little d. And that means that the circumference of this wheel is pi d, and the circumference of this wheel is pi times 4d. In other words, it's 4 times the circumference. Now consider what happens. Every time you do one revolution of this wheel, you will cause this wheel to turn 4 times. Because essentially the rope will go through a complete cycle. You will get pi times 4d of rope going round in one cycle. And in order for pi times 4d of the rope to go round this wheel, the wheel will need to turn 4 times. So you've got a gearing ratio of 4. You turn this wheel through 1 revolution, it causes this wheel to turn through 4 revolutions. So here's a way of getting a small wheel to turn very fast, rather than you pedalling the small wheel, which means you'll have to pedal very fast to get it to go fast, you can now pedal at a much more relaxed rate on a big wheel, because every single rotation of that wheel will cause 4, in this case, rotations of this wheel. So you don't need to pedal so fast in order to get this wheel to turn quickly.